Okay, so good evening, everyone. I hope I am audible to everyone. Can anyone confirm if I'm audible or not?
Yes, you're audible.
Okay, thank you. So, today we will be doing the live session of week 2 for the course Nonlinear Vibration, NOC25 ME57. And this course is being taught by Professor S.K. Dwivedi, IIT Guwahati, and I am Rashi Aditi Ranjan. I am an NPTEL PMRF TA. And in this live session, we will be taking up questions and concepts which will be useful for you to solve your assignment problems. And so we'll start with today's live session. So as you people must have attended the lectures and you must have gone through these following topics as the professor has taught. So, okay, so I'll be giving you a brief overview about these. Okay. So, as you know that if we want to work on a physical system, what do? We try to obtain its equation of motion, right? Because through the equation of motion, we can actually talk about the behavior of the system, its dependence on the parameters, and many further things, right? Now, coming on to how do we derive the equation of motion? Okay, so for a non-linear system, we have essentially two ways of deriving the equation of motion. Yeah. What are those two ways? One is the lumped parameter model approach, and the second one is the distributed mass model. Okay, so there is essentially two things. First is a lumped parameter model. What do we mean by the lumped parameter model? We consider that our system is actually divided into a number of n series of mass, spring, and damper. Okay, we consider it as a summation of all this. Okay, while in case of a distributed mass, like for a lumped parameter model, we have a spring and a mass. So this is a lumped model. Okay, when I talk about a distributed mass model, what I mean is if I consider something like this. Now, if you see here, the mass is actually distributed among the length of the rod, right? Here we have a mass which is concentrated at a point, right? We consider it that the mass is concentrated at a point. While in case of a distributed mass model, my mass and the stiffness is actually distributed among all the body, right? So for a lumped model, we have finite number of frequencies, while in case of a distributed mass model or what we call a continuous body, we have infinite number of frequencies, right? So essentially what do? We actually try to model a continuous body in the form of a lumped model because it is much easier for us to deal with, right? However, the best model is anyways the distributed mass or the continuous model, right? Now coming on to that, how would I derive the equation of motion? So essentially this is broadly divided into two categories. One is force or moment based approach. Now what does it mean? Here we consider only the forces and the moments. Okay, and then we derive the equation of motion. Now it has two laws. First one is the Newton's second law and the second one is the D'Alembert's principle. Newton's second law, you all know, summation of all the forces is equals to summation of mass into acceleration. This is your Newton's second law, right? Simple and easy. D'Alembert's principle is a special case of Newton's second law, wherein what do? We consider that our inertia forces is also an integral part of the system, which means that if I consider some F, let us say inertia E is equals to minus of summation of, then we have This is your D'Alembert's principle. So what does the D'Alembert principle do? The D'Alembert's principle actually convert my dynamic system into a static system. Okay, and if I convert it in a static system, then I can apply the principle of virtual work and all those to derive the equation of motion, right? So these are the two laws. Second one is the energy-based approach. Now the energy-based approach is then classified as Lagrange equation and the extended Hamilton principle. So Lagrange equation and extended Hamilton's principle, in this what do? We actually calculate the kinetic energy, we calculate the potential energy, then we derive the Lagrange, which is essentially kinetic energy minus potential energy. Okay, then we have the Lagrange equation, which says that del dy dt minus partial differential with respect to q. Okay, here capital Q is my generalized force and small q is my generalized coordinate. Okay, and if I talk about the Hamilton's principle, my Hamilton's principle says that integral from t1 to t2, this is my Hamilton. Actually, it's the uh, Hamilton's principle. In case of extended Hamilton's principle, we also have minus WNC, which is the work done by the non-conservative forces included in it. So if we do not consider this non-conservative part, we call it the Hamilton's principle. If we consider the non-conservative part, we call it the extended Hamilton's principle. Okay. In case of Lagrange equation also, we have a Lagrange equation in which we do not consider the my screen is not visible. Uh, I think you should check your connection once because it is visible to other people and it is visible to me also, like in my laptop. Maybe you can rejoin again because okay. So okay. So these are the two approaches, and I hope that the concept of generalized coordinate is clear to you all. See, we have two things. One is the physical coordinate, and the other one is the generalized coordinate. So, for example, if I consider a simple pendulum like this, okay, so it is actually oscillating in the plane, xy plane, right? But we usually write its equation in terms of theta, which is actually the angular displacement with respect to the vertical line. Yeah, why? Because this length of the pendulum is constant, because of which, if I consider the x and y, I have this constraint relation x square plus y square is equals to L square, because of which I can actually find a relation between x and y, and I can see that x and y can be related to each other, right? So x and y as my physical coordinate, and hence I convert it into generalized coordinate, right? Where generalized coordinate is nothing but theta, because my x is equals to L sine theta and y is equals to L cos theta minus, right? So I convert it into the generalized coordinate because it then makes my problem easier, right? Okay. So we usually, whenever we apply the energy based approach, we try to find out first our generalized coordinate and then we apply the equation using the generalized coordinate only, because in that way I can obtain my equations in an easier way, right? Because in case of a simple pendulum, if you see, I earlier had two physical coordinates, so that would make my equation a 2 degree of freedom system. But then I see that there is a constraint, which means that my system is essentially a 1 degree of freedom system and not 2 degree of freedom system. Okay, so if it's a 1 degree of freedom system, it is better to work with a generalized coordinate. Now, these methods are actually based on the approach that my coordinate is actually fixed. If my coordinate is moving, then I can further use the Newton-Euler formulation and the Lagrange-Euler formulation for obtaining the equation of motion. Okay, I hope this is clear. Anyways, this has been discussed in a very elaborative way in the week 2 lectures. Okay, so I'll be going to the question now. Okay, so my first question is this, where I have a 2 degree of freedom system and I have a forcing on mass m2 and I have to evaluate its equation of motion, considering that my stiffness is essentially nonlinear. Okay, here it should not be stiffness actually. Wait. Here it should be spring, force F1 and F2. Okay, now, okay, so this is my system. Now this is a 2 degree of freedom system, right? This is not a 1 degree of freedom system because we do not have any kind of a constraint in which I can relate x1 and x2, right? Now see, here I've already mentioned that we have to use the Newton's second law. Okay, so if I am using Newton's second law, I need to do the force balance, right? For that, what do I need? The basic step for applying Newton's second law is to draw the free body diagram. Okay, so if you draw the free body diagram, it becomes easier for you to solve the question. So we'll be first drawing the free body diagram. For mass m1, I have the extension x1. I have the inertia force m1 x1 double dot, right? Now see, for the time being, I'm considering that my spring force is linear. Okay, so what are we going to do? We'll first consider that my spring force is linear. Okay, once I will be able to find the equation with a linear spring force, then what will I do? I will replace that force with the nonlinear force. Okay, so if I consider that my spring force is linear, I'll have a spring force K1 x1 like this, and because of the spring that is below it, which connects m1 and m2, if I see this spring, which is K2, what is the extension? See, here it is getting extended by x2, here it is getting compressed by x1. Okay, so its total deformation is what? X1 minus x2, right? Mind it, this is the displacement direction and not the force direction. Okay, so in that case, what is going to happen? If it is compressing like this, it will apply the force in the upward direction, right? So here there will be one more force which will be equal to K2 x1 minus x2, right? So my free body diagram is complete for mass m1. Now if I come to mass m2, for this mass I have x2, okay? Then I have again the spring force, right? Like this, if I consider, it will be K2 x1 minus x2, and I have inertia force which is m2 x2 double dot. Okay, so now I can get the equation of motion. But what do I have to do? I have to consider the nonlinear spring force, right? So what will I do? I will simply replace whatever my spring force is with the spring force that is already given in the question. Okay, so for the mass m1, everything will be same. See here it is k2 x1 minus x2 and the direction is in the downward direction. If I take it in the upward direction, it will simply be k2 into x2 minus x1. Okay. Now see. Now I will replace this k1 x1 with what? I will replace this with k11 x1 minus k12 x1 square. Okay. And this force I'm going to replace with k21 x1 minus x2 plus k22 x1 minus x2 whole cube. Simple. I hope there is no doubt. We have simply replaced the linear force with the nonlinear force. Okay. So here also I'll replace this with k2 1 x2 minus x1 x2 minus x1 because that x1 minus x2 was in the downward direction. Now I'm considering it in the upward direction. Okay. Plus k22 x2 minus x1 whole cube. I hope it is clear. There is no doubt in this. Now what will I do? I'll simply write the equation of motion. So for mass m1 x1 double dot. Okay, this inertia force is taken in the upward direction. I hope you people understand that since the displacement is in the x1, like it is in the downward direction, the inertia always tends to take the system to the state it earlier was. Okay, so the inertia force is going to act in the opposite direction of the displacement. So that is why we have taken the inertia force in the upward direction. Okay, m1 x1 double dot plus k11 x1 minus k12 x1 square plus k21 x1 minus x2 plus k22 equals to 0. Okay, there is also one interesting thing that you people should note that my spring force for the spring number 1, the spring is actually softening type because you see a negative sign over here, right? While in case of spring 2, the spring force is hardening type, like I discussed in the previous live session, that a spring is essentially linear and nonlinear, and the nonlinear spring is further of two types, hardening type and softening type. Hardening means that after certain time of displacement, the further displacement is very difficult, while in case of softening type, the displacement becomes easier and hence instability is more in case of a softening kind of spring. Okay, now for the second mass, we'll have m2 x2 double dot, and there was plus k21 x2 minus x1 plus k22 x2 minus x1 whole cube is equals to, yeah, there is one more thing that I left over here with m2, which is f sine omega t, the force in term. It is also important, f sine omega t, right? So we'll equate it with f sine omega t. So this is my second equation. I hope this is clear. This was a very simple thing, but I thought that we'll just discuss it so that it will be easier for you to find the equation of motion, right? So if in case you have any question that has that the mass of the spring is given, the damping of the spring is of the dashboard is given, and after that the spring force is given, which is non-linear. So now I guess you people can solve the equation. So what do you have to do? You just have to remember that for a spring mass system, the equation is of the form like this, right? The equation is of the form like this. And if you have the spring force, which is nonlinear, what will you do? You'll simply just replace this with the nonlinear spring force. Okay, you can do that. Apart from that, what if your damping is also nonlinear? So you replace with that the nonlinear term. And if your mass, let us say mass is dependent upon x, then you can simply replace this mass with that term, right? So I hope that this is clear with you all. And there's one more thing. What if you have a question where in a general form of the equation is given? Like for example, you have f as ax plus bx square plus cx cube plus dx to the power 4. You have a generalized form, and then you have to evaluate these constants. So I guess you can solve it since, for example, you have the data of x. At x1, you have force F1. At x2, you have force F2. At x3, you have force F3. And at x4, you have force F4, right? So what will you do? So if you see, it's a linear equation. X is known to me, x1, x2, x3, x4. And corresponding to that, I have the value of the force F1, F2, F3, F4, right? And there are four unknowns. You have unknown A, B, C, and D, right? You have four unknowns. So what will you do? You will simply obtain the four equations. Okay, you have four unknowns, and then you can solve it. It's a linear system. You can solve it on your own also. You can solve it using MATLAB also. Okay, in MATLAB you can solve it. You can define it in a matrix form, and then you can solve it. Okay, so I hope you'll be able to attempt the question. Coming on to question number 2. Now in question number 2, again we have a system, and we do not have a nonlinear spring force in this case. What do we have to do? We have to actually learn the use of Lagrange equation and the Hamilton's principle in order to obtain the equation of motion. Okay, and then we'll cross check also whether these two rules are actually giving me the same equation or is it giving me the different equations, right? So firstly, what I'll do, I'll take the coordinates. So I have two generalized coordinates. Why? Because it's a 2 degree of freedom system, right? So my generalized coordinate x1 and x2. Okay, x1 and x2 are my generalized coordinates. Okay, so coming on to, let us do one thing. Let us first evaluate the kinetic energy and potential energy and take out the Lagrange, and then we'll see what are these two rules by which we have to evaluate the equation of motion. So my kinetic energy is going to be simply half m1 x1 dot square plus half m2 x2 dot square, right? Okay, coming on to potential energy. Okay, here again we know that this spring K2, here we have a displacement of x2, here we have a displacement of x1, right? So the actual displacement will be x1 minus x2, total displacement of this spring K2, right? So my potential energy is essentially stored inside the spring. For the first spring, it will be half into k1 x1 square. Okay, and for the second spring it will be half into k2 x1 minus x2 square. Okay, now by this I can evaluate the Lagrange. L is equals to kinetic energy minus potential energy. Right? What will it be? Okay. Now I have two ways by which I have to find out the equation of motion. One is the Lagrange equation. Now what does the Lagrange equation say? The Lagrange equation says that d by dt of partial differential of Lagrange L with respect to generalized velocity minus partial differential of Lagrange with respect to the generalized this displacement is equals to Q, which is the generalized force, right? While what does my Hamilton principle say? It says that the integration of delta Lagrange with respect to time dt from t1 to t2 is equals to 0. Okay, minimum action rule. Okay, so we'll first use the Lagrange equation. Okay, so by Lagrange equation, what will I do? I'll apply the equation. Now see, since I have two generalized coordinate, I'll have to apply the Lagrange equation two times for both the coordinate. Okay, so my first approach will be d by dt, partial differential of this with respect to x1 dot minus partial differentiation of L with respect to x1 is equal to 0, because as you can see in the equation, we have no generalized force over here, right? We don't have any generalized force. So this will be equal to 0. And for the second generalized coordinate, I'll have d by dt del L by del x2 dot minus del L by del x2 is equals to 0. Okay, these are the two equations, 1 and 2. So using 1, what do I get? I'll have d by dt partial differential of L with respect to x1 dot. It will be what? You see here, there is only one x1 dot term over here, right? So we'll have the differentiation which will be twice of x1 dot. 2 will cancel out, so it will be nothing but m1 x1 dot minus, what will I have? See, I have minus, wait, here it will be minus and not plus. Okay, so if I'll differentiate this, what will it be? It will be k into x1 minus of k into x1 k1. And for this, what will I have? I will have k2 x1 minus x2 and into 1, right? So minus, yeah, will be equal to 0. So partial differentiation of m1 into x1 dot. There is one thing that I would like to tell you, that for this equation also, like I did two things. Okay, first is the del L by del x1 naught. Now second one, I have this d by dt m1 x1 dot, and third one is I did del L by del x1, right? In all these differentiation, I considered that my stiffness as well as my mass are constant values, right? I have not considered them to be dependent on my displacement, velocity, or time, right? That is why it is coming out of the differentiation. It is not getting differentiated, right? But this is not actually the case for a physical system, right? For a physical system, you all know uniformity is an ideal assumption that we take, right? I'll take a slab of marble or of metal sheet, anything. I consider that the mass is homogeneously distributed. Okay, it is uniformly distributed. But is it actually true? No. There is always some manufacturing defect, right? Or maybe some human error, because of which there is some difference in between the mass, how it is distributed, or the property of the system. Like if I talk about stiffness, it would depend upon how my molecules are distributed among the system, right? So this is a generalized assumption. While in case of the materials that are being used now, we are actually focusing on materials that actually show varied properties, right? Because then it is going to give us more advantage. Okay, so we are actually working on it. So, like for example, we consider a functionally graded material or maybe some other material, like I discussed about a magnetoactive polymer, right? So, for a magnetoactive polymer, what happens? If I change the magnetic field, my distribution of particles inside the material changes, right? So if the distribution changes, if the orientation changes, it would actually change the density. It will change the stiffness, definitely. So in that case, when I'm doing these equations, when I'm following these equations, it is important that I consider those properties. Okay. So in that case, my mass or stiffness will remain inside the differentiation. It will not come out as a constant. Only if I consider an ideal situation, then only I can consider the mass or the stiffness to be constant and take it out of the system which I am doing currently. I'm considering an ideal system. Okay, but that is not true for all kind of a system. Okay, so if you have some problem in which you have to consider the property of the material, the structure of the material, or the mass distribution of the material, the particle distribution of the material, in that case, your mass and stiffness are going to be inside the differentiation. Okay, either you consider mass as a function of time and velocity and displacement and keep it inside the system, or if you have the equation of mass, stiffness, or any of these kind of a property in terms of time, in terms of velocity, in terms of displacement, in that case, what you can do? In that case, you can just differentiate it and write the full equation. But it is very important that you know that if it's not an ideal situation, you should always keep these values inside the differentiation and not treat it as a constant. Okay. Okay. Now coming on to this. Okay, maybe I should write it so that you'll remember. Here mass and stiffness are considered to be constant and not dependent on the time or displacement. Okay. Now coming on to here. So we will get the first equation of motion as m1 x1 double dot plus k1 x1 plus k2 x1 minus x2 is equals to 0. This is my first equation of motion. For the second equation of motion, we're going to have d by dt m2 x2 dot, similar to what we did earlier, minus uh, okay, here if we differentiate this, we are going to have half, okay, k2 x1 minus x2 into minus of x2 minus of 1. Okay, we'll have a plus because k2, when we differentiate x2, it will give us minus 1. So we will have k2 x1 minus x2. So we'll have the equation of motion as m2 x2 double dot plus k2. Okay, we have changed from x1 minus x2, we have changed to x2 minus x1. Okay, so it will be a plus over there. So this is my second equation of motion. Okay, I hope it is clear. So these are the two equations that I have obtained from the Lagrange equation. Okay, now what will I do? Now I will go to the Hamilton's principle. Okay, so as I discussed over here also, that my Hamilton principle says that the delta of my Lagrange integration with respect to time from t1 to t2 should be equal to 0. Okay, so now if I evaluate, first I'll just evaluate delta L. Okay, now again, since I have considered my m1, m2, k1 and k2 as constants, so what will I get? I will get half. Okay, I'll just write it so that you have clarity. Although I could have skipped the step, but I'll just write it fastly. Let us write it as of now in generalized form only. Half k2 twice of x1 minus x2. Okay, and then inside it is going to be delta of x1 minus delta of x2. Okay, this I can further write as, now see here I have x1 dot, which is d by dt of x1. So what I can do, I can bring the d by dt outside. Okay, so then what will it give? And I'll cancel the 2 from everywhere. So this will give me m d by dt delta x1 m2 x2 dot d by dt delta x2. I hope this is clear. We have just taken the d by dt out. Okay. Okay, so let us just consider the first term as of now. The first term. This I have to put inside the integration. Okay, let me just write the integration equation, then we will come to the first term. So for the Hamilton's principle, I have integration from T1 to T2 of this equation, which is M1 x1 dot d by dt M2 K1 x1 K2 x1 minus x2 into dt equals to 0. Okay. Now if I consider only the first term, okay, let me just focus on the first term as of now. What do I have? I have integration okay. What we can do? We can apply the rule of integration where we have two variables in product. So what do? First we do is first function into integration of second function. So d by dt, integration of d by dt is what? Whatever the function is, that delta of x1, limits of integration from t1 to t2, minus integration of differentiation of first function, which is m1 x1 double dot, into integration of second function delta x1 into dt from t1 to t2. I hope this is clear. Okay. Now, if you remember the lecture wherein this was discussed about the Hamilton's principle, then you know that the variation delta x1 is what? It's the variation, right, from the path. So it is considered that this variation at the end points are equal to 0, right? So T1 and T2, the value of delta x1 at T1 and T2 are what? They're equal to 0. Hmm? So we have m1 x1 dot 0 minus 0. This goes to 0. So I just have this term remaining, right? Similarly, coming on to the second one, I can also write this in the same form. T1 to T2 m2 x2 dot d by dt delta x2 into dt. This will simply be minus T1 T2 m2 x2 double dot delta x2 dt is equals to what? Nothing. This is only what we have. And there is one mistake that I have done over here. Here, there will not be a plus. Instead, it will be a minus, because the Lagrange's kinetic energy minus the potential energy. Okay. Now what I'll put it in the main equation. This is my main equation. Let us call it as 1. Putting the above equation in 1. What will we get? Okay, I'll try to write it again. there was integration t1 to t2 minus m1 x1 double dot delta x1 minus m2 x2 double dot delta x2 minus k1 x1 delta x1 minus k2 x1 minus x2 delta x1 delta x2 whole into dt should be equal to 0. Okay. Now what will I do? I'll try to separate the variation of x term and the variation x1 term and the variation of the x2 term. Okay, I'll try to separate it. So what will I get? I'll have again two things, t1 to t2 this whole because here is a minus, so this will get converted into plus equal to 0. Now since this x1 and x2 are two independent parts, okay, so its integration, both the integrations are going to be 0. Okay. Now since the variation delta x1 delta x2, these are what? These are arbitrary constants. Okay, it's a value. It is only 0 at the end points at t1 and t2. Other than that, it is not equal to 0. Okay, but the integration is equal to 0, which means what? Which means that my this term is 0, this term is 0. Okay, so if I equate it to 0, what am I going to get? m1 x1 double dot k1 x1 is equals to 0. And from this, I'm going to get m2 x2 double dot minus k2 x1 minus x2 is equals to 0. So I'll change, I'll make it plus, I'll make it minus, and I'll make it plus. These are my two equations. If you compare this with what we got with the Lagrange equation, you'll see this and this exactly the same. Second equation, this exactly the same. So what I got? I got that if I apply the Lagrange equation or if I choose the Hamilton's principle, both ways I'm going to get the same equation of motion. Now which equation do I have to choose? It wholly depends on me. Okay, whichever I am comfortable with. Okay, because it's maths. So whichever I'm comfortable with, I'll choose that equation, right? So this is it. Okay, so I've already discussed the dependence of the parameter. Like, for example, if I have some parameter and I have to see the dependence of mass and stiffness, then I'll just not consider it as a constant and I'll have to consider its differentiation as well. Now here I want to discuss one thing that, for example, if I have a pendulum, I have a simple pendulum. I have a simple pendulum which is attached here, and my support is actually oscillating. My support is oscillating, let us say as A sine omega t. And this I define as theta. Okay, no, I'll consider my support is oscillating not vertically but horizontally. It is oscillating horizontally with a sine omega t. Okay. What if I want to calculate this equation of motion? What is going to be the approach? I'll not solve it completely. I'm going to show you the approach. Okay. So here, what am I going to do? I'll consider that, okay, I'll have two displacements. One is going to be in the x direction and the other one is going to be in the y direction. So if I write my displacement in the x direction, it is going to be what? See this. This is L. So I can take the component over here, which would be nothing but L sine theta. So I'll have L sine theta plus A sine omega t. And I have y as minus of L cos theta. Right? I can write it that way. So these are the positions. Now what I can do, I can find the velocity by differentiating both with respect to time. My theta is dependent on time and my this oscillation x is actually dependent on time. So I'll differentiate. What will I get? X dot L theta dot. Differentiation of sine theta is cos theta plus A omega cos of omega t. And y dot is going to be L sine theta theta dot. Right? Now, if I want to find the total kinetic energy, what I can do? I can write it like the kinetic energy as half m, this is of mass m, x dot square, y dot square. Correct? I hope there is no problem in this. Half m, x dot square, L square, theta dot square, cos square theta, plus a square, omega square, cos square omega t, plus 2 L theta dot a omega cos omega t plus L square theta dot square sine square theta. Correct? This and this, if we add cos square theta plus sine square theta, will give me what? 1. So I'll have kinetic energy as okay. Potential energy, nothing but minus of m g L cos theta. I consider that here I have zero potential, so in the negative direction minus. I have kinetic energy, I have potential energy. I can simply apply the Lagrange equation or the Hamilton's principle and get the equation of motion. I hope there is no doubt. I'll not solve this equation fully, but I think you people can solve it. Okay. So I've just given you an idea that how you have to deal with this problem. See, the difference was that earlier where I had a spring mass system, I had a forcing function, right? So in case of a forcing function, what do? I define the force as the generalized force in case of the Lagrange equation, and then I find the equation of motion, right? There I consider it as a generalized force. However, in this question, my A sine omega t is not actually a force, it's the displacement of my support. The support is actually getting oscillating at A sine omega t, right? It's actually the displacement with time. So that is why I have to consider it into the coordinate and calculate the kinetic energy on the basis of that. However, if it would have been a force, the approach would have been different. Okay, so if in case instead of the force you for a mass or any kind of a system, you have the displacement of this form, what are you going to do? you're going to consider it in the kinetic energy and the potential energy term. However, if you have force, you can consider it in the generalized force form. I hope this is clear. Okay. So then you can solve this equation. I'll not go into elaborative way. It was just to give you an idea. Coming on to this equation. Okay. So from here onwards, I would like to introduce the symbolic tool in MATLAB and like see we derive the equation of motion by hand. But what if my system is very complex and I don't want to go into the mathematics? So in that case, I can use the symbolic tools of MATLAB in order to find the equation of motion. Okay, so we are going to solve this question over there. Apart from that, other questions are also like that only. Uh, yeah, okay. So I'll,
Excuse me.
yes,
So right now for the assignments we are using MATLAB, but during the final exam, will we also have the option to use MATLAB or?
this I don't know actually. Whether you'll be having the questions in MATLAB or not. For that, I think you should write a mail to the NPTEL support team because
Yeah. Okay.
I don't have any idea about the portal.
Yeah. All right. Thank you.
Okay. So from now onwards, we'll be taking the question of MATLAB. So I'll just okay. So is my screen visible? I'm assuming my screen is visible. So okay. So this question, we have a given function. Okay, and we have to use the MATLAB symbolic tool to find the value. Okay, so first we'll define. So for that, what we need to learn is the SYMS function that is used in MATLAB. So by SYMS function, what do? We actually define a symbolic variable. Like see in MATLAB, it's basically a matrix or an array in which we define a variable, right? MATLAB always takes the input as a array or a matrix, right? But in this case, that is not true. We want my y as a function y only. Okay, I want it as y, the variable. I don't want to give it some value. Just in case if I want to assign it some value, then I want to have that. Otherwise, I want it as a symbol. Okay, so what are we going to do? We just open MATLAB. Okay, sims y. See, you can see over here in the workspace. See, y is defined as a 1 cross 1 sim. Again, 1 cross 1. 1 cross 1 is actually the size of the matrix, and sim is the symbolic function. So now my y is defined as a symbolic function. Now, if I define any of the function in terms of y, that function is going to be saved as a symbolic function. It will not have a value. Okay. So for the given equation, y e to the power minus y plus sine of 20y. So we'll define it. We'll assume it as f y into exp. So in MATLAB, the exponential function is actually defined as exp f plus sine of 20 into y. Let me just cross check. Yeah, it's fine. We'll do enter. See, it has already defined my equation here. And it has also defined it over the workspace also. Okay, this is my function. So now I know how to define a function in MATLAB using the symbolic variable. Okay, now comes the other part of the question, which says that the value of this function at y is equals to 10. Okay, so I have to evaluate the value. So what will I do? Now there is a function, a command in MATLAB, subs, subs. We use it to actually find the particular numeric value of a symbolic function. Okay, so first I have to define y is equals to 10. See over here, it has changed the value of y. Earlier it was a symbolic function, now it is assigned the value y. Now I'll apply subs f. See, it has given me the value. However, you need to focus on the fact that even if I have tried to evaluate the value of my function at y is equals to 10, but it has saved like ans, like in MATLAB, if I do not specify a command, a particular variable name, it is going to save that currently as ans answer. Okay, but it will keep replacing it. Okay, like for example, if I give another command and I don't specify a variable, it will replace that answer with the current answer. Okay, so here if you see ans, it's again a symbolic variable, but I want it in a numerical value. So what will I do? So I'll use the command double, double, double of ans. See, it is going to give me the numeric value in decimal form. Okay, so this is how I can actually work with the symbolic tool in MATLAB. See, this was a very simple function. Okay, however, if I have to evaluate the value, I cannot evaluate by calculating on myself. I'll need a calculator. Okay. But if I go in a much complex domain and in a much complex equation where we have a various number of variables and those are all interrelated in the function in nonlinear form along with the very high power of polynomial, and it also has the sinusoidal function, cos function, exponential, logarithmic and everything. In that case, if I use a calculator, it's a very hectic task and there is a chance of human error also. So in that case, we can use MATLAB so as to get the accurate solution. Because see, if it's a exam problem, it's easy. Okay, you can do it. But if it's a problem which is related to a practical application, okay. So in that case, it is very important that we consider even a very small error, right? Because if not, it could lead to any kind of a catastrophic failure. So in that case, we use the symbolic functions. We use these softwares wherein we can get the accuracy along with simplicity of solving those equations. Okay, so that is why it is important that we learn the symbolic tools because then it will make our life much easier. I hope that this is understood that how we are going to use the symbolic function to define this variable and then again to find the value. We are going to use subs command and then we are going to use the double command to change it from the symbolic value to the numeric value. This one is the correct option. About the code, when I'll upload the PPT, I'll add the code in this and then I'll upload the PPT. Okay. Now, coming on to question number 4. Now the question number 4 says that I have a function f of x, okay, which is a polynomial function, and I have to evaluate the value of integration as well as the differentiation. Now this is a very simple equation, and I have evaluated its integration from -2 to 2, okay, like this, and it is coming out to be 8, and I have also evaluated the value of the differentiation, okay, at x is equals to 2.7, and it comes out to be this. However, again, this is a very simple equation, right? What if it's a more complex equation? In that case, when we have to evaluate the value of differentiation or integration, it becomes difficult. So we will again use MATLAB for this. We'll evaluate, as of now, we'll evaluate the same function only, and we'll cross check that what are the error or what is the difference between the evaluated values. Okay, so first we'll apply clear all, which clears the workspace, and then we'll apply CLC, which clears the command window. Now, if you see here, my variable is what? X. Okay, so I'll define the symbolic variable X. Now I'll define the function f. 2x plus 1.5 x square plus 0.5 x cube. 2x plus 1.5 x square plus 0.5 x cube. It has defined my function. You can see in the workspace also. My x is a symbolic function, symbolic variable, and then my f is also a symbolic function in terms of the symbolic variable x. Right here I can see it also. Now, first I have to evaluate the integration. So for integration, we are going to use the command int. It is used for evaluating the integration. We are going to put f comma -2 comma 2. So what have I done? For I and t, I have given the input as f, which is my function which needs to be integrated. I have given the lower limit of integration -2, and after that I have given the upper limit of integration 2. So let us do one thing. For now, we will remove the limits of integration and see what I and t f is going to do. See, it has given me the integration, however, it is in terms of the symbolic variable only. Okay, since I have not given the limits of integration. Okay, now as soon as I give the limit of integration, which is I give comma -2 comma 2. First I have to give the lower limit of integration, then I have to give the upper limit of integration. I got the answer 8, and this answer is exactly same to what I got analytically, 8. Okay, now what? Now I have to find the differentiation at 2.7. So for finding the differentiation, what do I use? I use the command diff, diff, and inside the bracket I'm going to give f, which is my function, symbolic function. Enter. See, I got the differentiation. Yeah. Now I want to evaluate the value. So again I'm going to do what? Okay, let us do one thing. Let us define the diff of f as a variable capital D. I got the differentiation. Now I use the command subs again to evaluate the value of the differentiation at 2.7. So dv, the value of derivative, is equals to subs capital D, comma 2.7. See, it has given me the value in fraction form. And again, you can see that here a value is actually a symbol. It's defined in the symbolic form. So what will I do? I again use the command double, double, double of dv. Now it has given me the value in the numeric form, in the decimal form, okay, which is 21.0350. See, exactly same value. This is what I got over here also, right? I hope this is clear. The use of this is clear. Again, if you have a very complex system, you can actually use it to, yeah. So if you have a very complex system, you can actually use it to get the value of my differentiation and integration functions. Okay. There is one more thing which I would like to tell about the DIFF. So, for example, let us say I have a function with two variables x and y. Let us suppose I have two variables x and y, and my function is something like anything 3 into x to the power 4 plus x into y plus exp of minus y. Let us suppose this is my function. My function is dependent on both the variables x and y. Now, if I want to find the differentiation, so I have two variables and I have to find the differentiation. Now, differentiation could be with respect to x and the differentiation could be with respect to y. So, how will I get the particular differentiation? Now, if I apply diff of y, sorry, f, c. So, it gave me the differentiation of the function with respect to x, right? But what if I wanted the differentiation with respect to y? What will I do? I'll just give the command diff of f, comma, y. Now see, now I got the differentiation with respect to y. Similarly, for getting the differentiation with respect to x, I can give f comma x. Here also I got the differentiation with respect to x. Okay, so while using the diff command, if I have a system which has multiple variables which are defined by symbolic variables, so in that case, what we can do is we can find the derivatives with respect to the particular variable, or we can say that we can find the partial derivatives, right? Because in case of partial derivative, what do? We consider the other variables as a constant. Okay, so that is how you can use it. Okay, now coming on to the next question. I hope this is clear. Okay, this question wherein I have a spring mass damper system. Okay, and like this is a easy system. I can find the equation of motion easily analytically. However, if I have a very complex system and I want the symbolic function to help me to get the equation, how will I do it? So I'll take this example. So if I have a spring mass dashpot system which has a forcing F sine omega t, and I want to find the equation of motion using the symbolic system. So what will I do? So first, these are some basics like the Lagrange equation we have already discussed and we have solved the equation also. So this is the Lagrange equation. L is my Lagrange, Q is my generalized force. Now I have L as kinetic energy minus potential energy, wherein the kinetic energy is given as half m x dot square and the potential energy is given as half k x square. And I have q as f sine omega t, and f sine omega t is clear, I guess, because it's a forcing function. However, the damping force is also considered as my generalized force, because see, in Lagrange equation, we consider that the kinetic energy and the potential energy are all because of the conservative forces, right? But this damping is actually a non-conservative kind of a force. Okay, so in that case, we cannot use it in the Lagrange equation. So what do? We consider that my damping force is actually applying a generalized force. Okay. However, there is also a modification of the Lagrange equation, which is also known as the modified Lagrange equation, wherein we define the Rayleigh dissipative potential, and then we use that, uh, yeah, wherein we use the Rayleigh dissipative potential to actually find the potential of the dissipation, and that is further like added in the main Lagrange equation as a modified term, and its differentiation with respect to the velocity and addition of its differentiation Rayleigh dissipative potential with the velocity actually adds on the effect of the dashpot on the system's equation of motion. However, in this case, we have just considered the force due to the dashpot as a generalized force in the equation. Okay, so coming on to the PPT, this. So now we'll just simply implement it in MATLAB. Okay, see, like this. Again, we'll do clear all and CLC. Okay, so first is what do we have to define? Now see, here I have x as a symbolic variable. Fine. However, I don't know the value of the mass. I don't know the value of the spring stiffness. I don't know the value of the damping. I don't know the value of F. I don't know the value of omega or W. So what will I do? I'll just define it as my variables only. And at any point of time, I can specify the variable and find the value. Okay. So as of now, we'll define it as a variable like similar to that of X. The only difference is going to be that my this mass, spring stiffness, damping, F and omega, they are not going to be a function of time. However, I'm going to define my X as a function of time. Okay. So I'll give the command sims m k c f w. Okay, these will be written like this. However, my x will be written like this, x into t. See, by default, t is taken as a variable for time. Okay, so if I'm going to define my x like this, x in bracket I have t, this means that I'm saying the symbolic toolbox that okay, you define x as a function of t, where t is my time. Now I'll put enter. See, here all my variables are defined. Okay. See, what is interesting is that all are defined as symbolic variables. However, x is defined as a symbolic function. Yeah, because it's a function of a time. Okay. Now, what will I do next? I think I should define my velocity x dot, which is what? Differentiation of x with respect to time is velocity. Correct? So what will I give the command? Diff x comma t. Okay, x dot is. Now you see here, now my x dot is also defined as a function of time, which is differentiation of xt comma t. Okay. Okay. Now let us define the kinetic energy, which is nothing but 0.5 into m into x dot square. Correct? Half m v square. See, it has defined m into velocity ka square divided by 2. This is my kinetic energy. Again, you can see my kinetic energy is now a function of time, right? Defining the potential energy, 0.5 into K into C. My potential energy is nothing but half K x square. Again, my potential energy is a function of time. Now what? Now I think I should define the, you can see over here, my generalized force, which is this. I should define my generalized force. So my generalized force would be what? Q is equals to F into sine W into T minus C into X dot. We'll put an enter. Done. Now, what do we have to do? We just have to put the Lagrange equation now, and this is going to give me the equation of motion. Okay, so I'll put the Lagrange equation. Okay, for that, first I need to define the Lagrange. L is equals to Ke minus Pe, kinetic energy minus potential energy. See, I got kinetic energy minus potential energy. Now I'll define the Lagrange equation. So what was my Lagrange equation? It was diff of what? If you remember the Lagrange equation, okay, I'll show it here. Differentiation of this. First, I had the differentiation of Lagrange with respect to the velocity x dot, and then I had the differentiation of this whole term with respect to time. So if I want to write this in MATLAB, I'll write it how? Diff of something with respect to t, and this something is going to be nothing but diff of L with respect to x dot. You need to see it clearly. First, I have defined the differentiation of L Lagrange with respect to x dot velocity, and then I have defined another differentiation of this whole term with respect to time. Okay, then I have a minus, then I have diff of L comma with respect to x. Yeah, see, see, differentiation of L with respect to x. This is equal to q. Okay, the question is why double is equal to and why not single is equal to. So in MATLAB, when we say is equal to, it is essentially used to specify a particular value to a particular variable. For example, I'm writing x is equal to 2, which means my x is having a value of 2. X is equal to a array or a matrix. So x is having that value. If I define the symbolic function x as like I define m and something m into k, okay, and I define x is equals to m into k, so it will show that my x is actually a function of m into k. Okay, so f is, sorry, x is mk, sorry. So a single is equal to is essentially used to give a particular value, assign a particular value to that particular variable. But when we use double is equal to, it is essentially a equality of the left hand side and the right hand side, right? Like we use in mathematics, x is equal to 2 or LHS is equals to RHS. That means that LHS value is equal to RHS value. So in order to specify that to this software, we need to use 2 double is equal to. Okay, so here since we are making it equal, we are making the LHS equal to the RHS, and that is why we are using 2 is equals to, and we'll do enter. Now see, we have got the equation of motion. How? Let us just cross verify. We have m multiplied by diff of x of t comma t comma t. Comma t mean 2 times t means we have differentiated x with respect to t twice, which means what? Acceleration. Mx double dot. Then we have plus kx. Okay, is equal to what? F sine omega t minus c diff of xt comma t, which is velocity c into x dot. If you'll bring the c into x dot towards the left hand side, you'll get mx double dot plus cx dot plus kx is equals to what? F sine omega t, which is nothing but my equation of motion. I hope this is clear. There is no doubt. Uh, Similarly, now since this was a linear equation and it was easy to find out the equation of motion, we could have done it on our own also. If you get a complex equation, can you do it? I hope you can do it. I think it is very easy. In fact, it actually reduces the burden, okay, that we have to do while actually solving the equations, right? So I think that you people will be able to do it, right? Now, coming on to the PPT again, we have finally done it with respect to whatever. Okay. Now coming to question number 6. The question number 6 that using the equation of motion obtained in the previous section and considering m is equal to 1, k is equal to 2, c is equals to 1 and f is equals to 0, omega 0. The system attains the equilibrium point. See, if you look at this equation, this system, okay, you have an equation of motion. Equilibrium point, how do we evaluate the equilibrium point? In the equation of motion, if we make the velocity and the acceleration 0, we are going to get the equilibrium point. Here, if you are going to do it, you are going to get x is equals to 0, x dot is equals to 0 at the as the equilibrium point. Correct? So, for this equation, it is very easy that the answer is going to be b 0, comma 0. Okay. However, since this was a linear system and it was an easy system, you could do it. Okay. What if I introduced a non-linear term like this, which is beta into x cube? What is it doing? It is actually changing my spring force from linear to non-linear, that to hardening type. Okay. Now if I tell you that, okay, just find me the solution of this equation. Can you do it? You can do it, but as per the knowledge that you have currently, you cannot. You need to learn that how do we have to solve this kind of equation and then you can do it. Okay, so you can find the solution. However, it is a bit difficult for you to find the solution, right? So what are you going to do? See, in that case, we use the OD45. I discussed the OD45 in the previous live session also. However, I thought that I'll just give you a brief about how do we use OD45 because last time I just gave you the code and I solved it. However, I thought that I'll maybe discuss the logic with you all. So, see, OD45 is nothing but a numerical technique. Numerical technique, when we do not have a continuous solution of a function, we actually try to break it into discrete form, right? And when we break it into discrete form, we can actually use the numerical technique in order to find the solution, right? Like for example, I have a point in space and I know that, okay, the slope at that point is something. So what I can do, I can find the value, other value by just multiplying my x value and I can get the x value with my slope, right? Like I have dy by dx and if I multiply it with x, what am I going to get? I'm going to get the change in y, right? Similar concept is used for the numerical technique which are used to solve the like differential equation based problems. Okay, that if you have dy by dx, you are going to multiply it with x and then you are going to get the change in y and then you are going to add that change of y into the previous problem. Okay, so uh, which is fine. Okay, which is fine for me. Uh, but then that is when I have dy by dx. But for this equation, see here, this equation, I have mx double dot. Okay, I have the second differential of x also. How will I solve it? Now my RK4 method or my OD45 can solve dy by dx or it can solve dy by dt or it can solve dx by dt. How it is going to solve the second differential of x with respect to time, which is the acceleration. Now what will I do? Okay, so for that I need to do some work. Okay, so that I can feed in the input to the ODE45 and it is going to give me the output. So what will I do? I will change my, now this is a second order differential equation. Mx double dot, it's a second order differential equation. Now what will I do? I will say that okay, I'll just convert my second order differential equation into two first order differential equations. That is possible. If you have the nth order differential equation, you can actually convert it into n first order differential equation. And if I'm done with that, like if I have n first order differential equation, I can simply feed up ODE45. I can say that to the ODE45 that okay, I have n first order equations and these equations are actually interlinked to each other. They are coupled. So I would give that to my ODE45 as a command as an input, and then it is going to just simulate considering the coupling of those n first order equations and give me the solution. Okay. So similarly for this second order differential equation, I'm going to convert it into two first order differential equations. How? Like here. I will consider my variable as z, which will have two columns. Okay. Now those two columns, one column will be of the velocity, other column will be of the displacement. Okay. Why velocity and displacement? Because ODE45 is performing integration. Okay. I have the equation of acceleration. Okay. I want displacement. I have to perform two integrations of two equations. First equation is going to be of my acceleration. Second equation is going to be of my velocity. When both the equations are integrated, by integrating the acceleration, I'm going to get the velocity. By integrating the velocity, I'm going to get the displacement. Okay, so I'll define two variables. First is going to be the displacement and second one is going to be the velocity. So I define my z of 1 as x displacement and I define z of 2 as x dot, which is nothing but velocity. Okay, now what I can do? Now I can write the equation of motion. Why? Because I have what? Now I have two first order equations, differential equations. Because if you differentiate z1, if I define z dot, so 1 I can get as x dot and z dot of 2 I can get as x double dot, which I already know, right? Which I already know. Why? Because my z dot of 1 can be written as z2. Z2 I can write like here. You can see my z dot. First one is written as z2 because z2 is nothing but the velocity, right? Velocity I'm integrating to get the displacement. And now my z dot of 2, which is actually the differentiation of velocity, acceleration, I can find the equation like this. How? By this equation, by the equation of motion. By the equation of motion, if I bring everything on the right hand side and I can find a equation of x double dot in terms of x and x dot, so I can write it like this. Here z1 is nothing but x and z2 is nothing but x dot. So I wrote my acceleration as a function of z2 and z1. Now what? Now I've successfully done what I wanted to do. I converted my second order differential equation into two first order differential equations, which is coupled definitely. And this coupled equation I'm going to solve in order to get the solution. So we'll try writing the code. We will try writing the code. We'll open a new M file. Yeah, first I'll change the equation. Okay, Z2. I had Z2 over here. Yeah, and here I have 1 by m minus cz2 minus kz1 minus beta z1 cube plus f sine omega t. So we'll write it. We have 1 divided by m into c minus c z2 minus k z1 minus beta z1 cube plus f into sine w into t. I hope this is clear. No doubt. Here we define the function as ODE fun t comma z, and we are going to now specify all the variable names m comma k comma c comma f comma w comma beta. Okay, we have to specify those value over here. As of now, we'll take m is equal to 1, k is equal to 1, c is equals to 0.1, beta is equals to 0.5, f is equal to 0.5, omega is equal to 10. It's fine, I guess. Okay, so we have to specify the initial displacement. Let us say it's 0, 0. Everything is fine. Now, the same order in which we have defined the variables over here, you have to define those variable over here as well. Okay, and yeah, that's fine. We have given t as like this. Let's try if it will work or not. Yeah, the code is working. We have 3 plots. See, we got the solution. We have the position with respect to time, we have the velocity with respect to time, and then we have our position versus velocity plot. Okay, so this is how the system is going to behave. And you can see that the behavior is very different actually. That is because my nonlinear term is introduced in the system, and that nonlinear term is making my system a bit complex. Like for example, if I try to make it a bit simpler, and I take my beta value as 0 and see what happens. Okay, still giving the same. We'll change the parameter. We need to reduce the forcing. Now see, how is it behaving? It is behaving in a periodic fashion, right? However, there is some initial transient. After that, it is behaving in a periodic fashion, right? However, now if I introduce a very small value of beta, let us see how the system behaves. Not much change. Okay, this is going to suppress. You see, the value has reduced. Yeah, the amplitude has reduced. So that is how the system is going to behave. Now, if I increase the forcing frequency, like forcing value also, then it will show a bit different kind of a vibration. You see, the amplitude has also increased. And again, if I decrease the value of beta, see, you know why the vibration is having a small amplitude? Because if you remember, it's a hardening kind of a spring, right? So with more value of beta, it is actually letting the system have small value of oscillation. See here, it has again changed. So this is how you can simulate with the system, right? So I hope that it is clear that how you are going to write the load code like for the system. If you get any of the system, you can write the code, I suppose. You can take the reference from this also. Yeah. Okay. Now coming on to, yeah, this question I did in the last class also. However, I wanted to discuss some things about this question, so I have again taken this question. Yeah, here. Yeah. So I've already written the code and I've taken the code from what I've written. I'm not writing the code currently since it will take a lot of time. So you can take this code. I'll share the screenshot with the PPT. You can take the code and then simulate with the system. Okay. So now we will try to like simulate the system. Okay. So for the initial condition 1 comma 1 comma 1. So first, but I would like to see for some other value of this parameter 8 by 3. I want to check it for 1 by 3. Let us see what the response is going to be. Okay, okay. So can you see how the response is? Well, it's a periodic response. Hmm? It's a periodic response. You can see after the initial transient value, the response is periodic. How do I know if it is periodic or not? Okay, let's just change. Okay. We have got the plot. We'll change the value of the initial condition as of now, 0.001. We have just changed the first initial condition from 1 to 1.001. Okay, now we'll again simulate the system. See, did you see? It has completely overlapped whatever the previous solution was. There is no difference. Yeah, because the change of the initial condition was very small, right? Okay, let us just close it. I want you all to remember the value, the change of value. It is 0.001. Okay, just remember this. Now let us change the value to again 1 and simulate. And now we change it to 1.1. Can you see? The response is still the same. Yeah, the response is still the same. Uh, Maybe I'll change it to 1.5. See, the response is still the same. Maybe I'll change it to 2. See, if I'm going to zoom it, then I can see that there is now a slight variation. Yeah, there is now a slight variation that I can see in all these responses. However, if I say the variation, it's very less. Okay, and the variation is just because of the change of the phase also. Yeah, but I can say that okay, the variation is not much. The amplitude didn't change, right? The amplitude of the periodic oscillation didn't change, only the phase has changed, right? In the phase plane, the response is exactly the same, the steady state response. So what is this? This is a periodic response. Okay, well and good, fine. Now again, I will change this parameter from 1 by 3 to 8 by 3. And now I'll again simulate the system for the initial condition. Okay, sorry. Okay, now, do you remember? how much I changed earlier? 0.001. Now I'll simulate the system. Now see, you see the variation in velocity. It's actually not velocity, the figure 4, it's actually the variation of the second dimension, which is y with respect to time. Okay, so you cannot call it the change in velocity with respect to time. So if you see over here, initially there is not much change in the system response. However, around 20, okay, the value of time 20. After that, the variation is quite significant. And after that, the variation is actually that significant that if I like consider this, if I look over here, this my system was, supposed to be at a positive position, yeah, at this time, at 25. But now my system is essentially at a negative position at 25. Okay, so it's not a very small change, it's a drastic change in the position. Similar is the case with the velocity as well. So what is exactly is happening? Now what will I do? I'll again try to simulate the system. Now I'm going to consider a smaller variation of the change of the initial condition. Okay, first I'll simulate for 1, 1, 1. Now I'll change it to point 1, 2, 3, 4, 5. See, if you closely look to this, the value of the variation that I have given, it is 10 to the power what, 1, 2, 3, 4, 5, 6. 10 to the power minus 6. But you see the difference? Initially everything is fine, everything is same, but after that the change is drastic. Yeah, the change is drastic. What is this? This is your chaos. An aperiodic motion that shows very, very, very high sensitivity to the initial condition is chaos. And that is why we try to avoid chaos. There is a effect which is known as the butterfly effect, which says that flapping of a wing of a butterfly at one side of the earth can cause a tornado on the other side of the earth. This is what it is. You won't even feel if a butterfly is flapping in front of you. You won't even feel it, right? Because the variation is not that much. But as it travels miles and miles and miles, it creates a drastic effect, right? Such drastic effect that it can actually change the normal condition to a tornado. And similarly, if somewhere a tornado is happening, then the flapping of a butterfly can actually stop that tornado, right? This is what chaos is. And chaos is present everywhere in the system, on our earth, everywhere in the existence, it is present, right? Because we essentially live in a world where everything is non-linear. Okay, nothing behaves in a linear fashion. Linearity is actually an ideal assumption towards the physical being of the system, of any kind of a system. But nonlinearity is what is actually possesses, right? So for a nonlinear system, if I want to identify that where the chaos is and how the chaos is happening, and like from this example, I hope it is clear that we are clear with the concept that why do we don't want chaos? Yeah, because it has sensitive dependence on the initial condition, right? Such sensitive dependence can actually, like, I'll assume that, okay, at this point of time, my system should be at its maximum level. But if there is even a small variation in the system, it could actually go to the lowest level, which would actually lead to some kind of a failure or some kind of a catastrophic failure, right? And we want to avoid it at any cost when we are dealing with a physical system. Okay. So that is why I hope it is clear we need to avoid chaos. Now, how should we avoid chaos? How will I know that the chaos is there? So see, for a nonlinear system, if it's a three-dimensional system, the chaos is going to be there. Okay, but it would depend upon the parameter value. Like here, as I gave the example earlier where I was showing the periodic case, I didn't change the initial condition, but the initial condition was same 1, 1 and 1, right? What was different? The parameter. Here, I just close the figure first. See here, I had this parameter 8 by 3. What did I do? I changed this to 1 by 3, and for the same initial condition, when I got the response, it was periodic response, and I also saw it's dependent on the initial condition, and it was very like it was not dependent on the initial condition because I changed my initial condition from 1 1 1 to 2 1 1. Still, my response was the same. The only difference was in the phase. Okay. However, as I changed my this value of parameter 1 by 3 to 8 by 3 again, what happened? I got chaos. And my chaos was showing a very high dependence on the initial condition. Yeah, which I want to avoid, right? So when we are dealing with a non-linear system, we know that okay, maybe chaos can be there, maybe cannot chaos cannot be there because there is no analytical method to actually find out whether the chaos is there or not, or whether what is the value of the parameter where we can get chaos. Okay, essentially we try to get it by the numerical method. Okay, or we try to get the bifurcation diagram. So as I told you about a bifurcation in the previous live session, that with the change of some parameter value, we have the change in the equilibrium points, right? Similarly, for the dynamic case, with the change of the parameter value, we have the difference of the dynamic behavior. And if we get that bifurcation diagram, we know that, okay, for these parameter values, I'll have a periodic solution. For these parameter value, I have quasi-periodic solution. And for these parameter values, I have chaotic solution. So we avoid the parameter values for which chaos is there, right? So in order to like limit the chaos in the physical system, we need to do the analysis and or the dependence of the system on these parameter values. Okay, so these parameters actually play a very important role. That is why I took this example because I wanted to show that keeping the same initial condition but changing the value of the parameter from 1 by 3 to 8 by 3 actually took my system from periodic to chaotic. Okay, I hope this point is clear to you all. Yeah. After this, I've again taken this question of the Van der Pol equation, which I did in the previous live session also. I guess this would just clear to you all. There was no error in this. So I've taken this because I wanted to discuss that, this behavior which we saw in the Van der Pol equation, this is what we call as a limit cycle. See, in case of a spring mass system, which has the equation mx double dot plus kx is equals to 0. If I change the initial condition, what am I going to get? I'm going to get that the amplitude of the oscillation is going to change with the initial condition. Like, okay, we made the code now. Let us just run that only. We have f0, this 0. Okay. Let us see the response for 1, comma 0. Okay. This is the response, position, and phase space plot. Now what will I do? I'll maybe suppress this figure 4. I don't want it. Sorry. Now I'll change to 2. Now see what happened. My amplitude of oscillation changed from 1 to 2. Now if I again change it to 3, see what happened. So with the change of initial condition, the kind of periodic orbit that the system is following is actually changing. The amplitude is changing, correct? Okay. Now this is a periodic response. Okay, this is a periodic response. While in case of my van der Pol equation, there is something very interesting, you know. My system response is actually not dependent on the initial condition. If I change this initial condition to 1 comma 0, see, it is again coming to the same periodic response. Okay, let us just change this also to 3, 1 comma 3. Let us see. See, for any kind of an initial condition, my system is always coming to the same periodic orbit. Now, what is this? In case of a spring mass system, it was different. I was changing the amplitude, the initial condition, the amplitude was changing. Here, I'm changing the initial condition, but the amplitude is not changing. My transient response is changing, although, but my steady state response is the same. It is the same phase plot, right? Why? Because this is a limit cycle. For this system, there is existence of a isolated periodic orbit, isolated stable periodic orbit, which means that in the phase plane, there is only one orbit which is stable and it is isolated because there is only one orbit. Okay, for this parameter value set. Okay, so this is what we call a limit cycle, and limit cycle could be seen in many of the physical system in nature. Okay, so yeah, I hope this clears the concept of limit cycle. And this is it for today's live session. So I hope that you people understand or understood whatever the questions were there and everything.
I have one question.
Yeah, please ask.
So you were explaining about limit cycles, right?
Yeah.
So is it possible that a single system with multiple degrees of freedom, it can have more than one limit cycle?
Yes, definitely it can happen. Definitely it can happen.
Okay.
It can have
And
multiple limit.
also,
Yeah.
yeah, you can continue. I will ask the one next.
Yeah, what I was saying is it can definitely have multiple limit cycles, and it can also happen that those limit cycles are so close to each other that you are not even able to identify whether it's a periodic orbit or it's a limit cycle. But there is one thing which is important about the equation that I talked about, van der Pol equation. It's actually a self-excited oscillation. You know, when I'm saying self-excited, like for example, even if I for a like a spring mass system, if I take the initial condition as 0 comma 0, it is always going to remain at that, right? Because it's a equilibrium point. But in case of this, my van der Pol equation, even if I take the initial condition as 0 comma 0, na, it is always going to go to the periodic orbit. It means even if I'm giving it zero initial energy, it is again going to go oscillate for that limit cycle, right? Because it's a self-excited system. Okay, the system has the capability that it will increase the amplitude or it will decrease the amplitude, but it is always going to bring my system to that particular limit cycle, right? And for a multiple degrees of freedom, it can happen that it can have multiple self-excited cycles or it can have limit cycles. Okay,
Yeah, that was clear. Thank you. And also regarding this Lorentz exciter that you showed before
it's not
for the
excited,
chaotic
it's a
response.
Lorentz system.
Yeah, for the chaotic response.
Yeah,
So let's say we don't have the plot of our displacements, and
okay,
we only get the phase portraits.
okay.
So is there any way to identify chaotic response only from the phase portraits without seeing the time dependence?
Mm, see, the basic concept of chaos actually comes from the time dependence only. However, if you saw in the phase plot, it will cover more area and it will not have a neat response. Yeah, like for a periodic response, for the steady state, you're always going to have a neat response, a circle or maybe two circles or something like that. But in case of a chaos, you will never see such kind of a response. You will see that for a complicated, more complicated systems like the system that we work on, we are going to get like a random shape which is totally filled in color, like in case of a phase plot, because of chaos. Okay, so from that also you can identify. Second option is again you need to change the initial condition in order to like see whether the first phase plot and second phase plot is same or not. And like we do in case of like research work, when we come to the context of research, we actually compute a numeric value, which is the Lyapunov exponent. Okay, so we essentially give the argument that whether the response is chaotic or not on the basis of that Lyapunov exponent. Okay, so in the coming class, I'll discuss about what Lyapunov exponent is.
Yeah, okay, thank you.
Okay, any further question?
No, not from my side.
Okay. Okay. So if you have any other doubts, so you can ask in the next live session. So I hope everything, yeah, I don't think no one has any other question. So yeah, we'll end the live session here. Thank you for attending. We'll meet next week again. Okay. Bye everyone.